Hi class. Today we're going to start discussing the basic method that we're going to use for solving partial differential equations. This is the method of separation of variables. We'll start by discussing its application to the simplest equation we can consider, Laplace's equation in two dimensions. This equation has the form del squared phi equals 0. In rectangular coordinates then, in two dimensions, del squared phi is d squared phi dx squared plus d squared phi dy squared. That is, we're solving for a function phi, a function of two spatial variables x and y. Physically, phi could represent the electrostatic potential in some region without charge, or it could represent the steady-state temperature distribution in some region. So the question is, how is it that we use this equation to solve for the actual value of the function phi? We do this by making, at first, a very, very powerful simplifying assumption. We look for solutions of the form phi, which are independently functions of x times functions of y. This is the first time I'm going to say it, but it's very important to remember. I'll refer to this as standard lecture number 35. It's important to remember that we are not saying that every solution of Laplace's equation or every solution of a partial differential equation separates into a product of functions of the individual variables alone. Instead, we're looking for particular special solutions which have this form. We're going to use these solutions as the bases, like basis vectors, almost literally, to solve the most general problem. But we start by making the simplified assumption. If we start with the simplified assumption, we can plug this form into this equation. Is the following. If we plug this into here, we get the partial derivative with respect to x squared gives us an ordinary derivative of the capital X function with respect to x times the function y, plus the partial derivative of phi with respect to y gives us the function capital X times the second ordinary derivative of the function capital Y with respect to y. The sum of these things has to be equal to 0. We can simplify this equation by dividing by capital X times capital Y, that is the form of capital Phi we started with. So we have the equation 1 over x times its second derivative, x double prime, or d squared x dx squared, plus 1 over y times the second derivative of y double prime, is equal to 0. This combination, by assumption, is a function of x only. This combination, by assumption, is a function of y only. The only way that a function of x plus a function of y can equal 0 is if each of them is exactly equal to a constant. The only possible function that's both a function of x and of y is a constant. So the x derivative, 1 over x times x double prime, has to be minus the y derivative in order for the sum to be 0. And we're going to call the constant, for convenience, minus k squared. For the moment, we're going to assume k squared is greater than 0, as implied by the way we've written it. We could, as you can see from this minus sign, changing the sign of k just changes what we're assuming about x and y. So we'll return to that. The value of k is called a separation constant, and it's an important concept that we're going to get. Notice this is a function of two independent variables, x and y. We have one separation constant. There's a general rule that says, in terms of the number of independent components or coordinates one has, we're going to have one less independent separation constant than the number of those components, because there is a relationship implied by the equation. We can solve the equation for x. The equation for x is just a harmonic oscillator equation, so we can write the solution for x as a cosine kx plus b sine kx, or we can equivalently write it in exponential form. In most cases, we're interested in real quantities, and that's the more convenient form. The solution for y, assuming k is a real number, is an exponential e to the plus kx or a negative exponential e to the minus kx. Or we can equivalently use the combinations in terms of the hyperbolic cosine of ky and the hyperbolic sine of ky. Remember, the hyperbolic cosine of ky is just the sum of e to the ky plus e to the minus ky over 2. The hyperbolic sine is their difference, e to the ky minus e to the minus ky over 2. So any product of a function of this form times a function of this form, that is, phi is a harmonic function of x and an exponential function of y, where the dependence on x and the dependence on y is set by the same constant k. Any function of this form will satisfy Laplace's equation. It's worth checking that and just calculating the derivatives and making sure that you can verify that any function of this form satisfies the equation. But of course we have a problem. We've now introduced a number of independent constants, a, b, c, d, as well as this unknown separation constant k. How is it that we can possibly fix all of these things? But in fact, we have too many solutions, because any function of this form is a solution of Laplace's equation. In fact, because it's a linear equation, we can take an arbitrary sum of functions of this form and still get an equation. So how do we determine these unknown constants, k, a, b, c, and d? The way we do that is to impose boundary conditions. So it's useful to think about a physical situation. Suppose you're interested in the electrostatic potential in a square region where you set the electrostatic potential equal to 0 on 3 sides, and you set the electrostatic potential equal to a constant phi 0 on the upper side. And this square region or plate has side L. And what we want to solve is for the electrostatic potential phi of x and y inside. That's what the partial differential equation allows us to determine. After all, you could imagine actually physically taking a square plate and fixing the sides of the potential to 0 on these 3 sides and to some constant potential on that side just by clamping the appropriate kinds of leads. Then the potential inside has to be uniquely determined, and that's given to us by Laplace's equation. Mathematically, the boundary conditions say phi at x equals 0, which is this side, or x equals L, which is this side, are strictly equal to 0. And phi at y equal to 0, which is this side, is equal to 0. And phi at y equal to L is equal to phi naught. So the first question we ask is, can we make our previous simple solutions, those separated form, which are a product of x times y, work? And what we'll see is for these 3 sides, we can easily make it work. If we set phi of x equal to 0, that's x of x equal to 0 times a function of y. If this is to be 0 without being trivial, then it must be that the value of capital X at x equals 0 equals 0. Similarly, if I apply the boundary condition at the right-hand side, we see that the function capital X at x equals L has to be 0. If we plug in x equals 0 into our form of the solution, we get a times cosine k0 plus b times sine k0. Since this is 0, this just gives us the value of a has to be 0. If we do the same thing for x equal to L, we set b sine kl equal to 0. We have 2 choices. Either b equals to 0, which would give us a very trivial solution, phi equals 0, which actually can't possibly satisfy this boundary condition here. Or we can say k is determined so that sine kl equals 0. That is, k is n pi over L, where n is an integer, 1, 2, 3, etc. A positive integer, because a negative integer just changed the overall sign, and n equals 0 would give us 0. We see that applying this boundary condition on this finite region from x equals 0 to L actually fixes the values of this separation constant. We don't get one value, we get many values, but they must have this particular form. This is called quantization. You may be familiar with that in terms of quantum mechanics. It's the same general principle, applying the boundary conditions to these unknown coefficient separation constants that occur in separation of variables, actually quantizes or fixes the values of k. While it fixes the values of k, there's still an infinite number, so we have some more. What about y? We can apply the boundary condition at y equals 0. Let's use the Sinch and Cosh form. It's convenient in this case because Cosh is always equal to 1 at 0, so this tells us c prime equals 0. From the last page, we know then that if we set this equal to 0, if we take any function of the form sine n pi x times sinh, what's left over in the y direction, sinh, the hyperbolic sine of n pi y over L, any function of this form satisfies not just Laplace's equation, but also 3 out of 4 of the boundary conditions which are equal to 0 on the left and the right and the bottom side. But we still have one more boundary condition. The value of phi at the upper end has to equal phi naught. None of these solutions work. But this is a linear equation, and therefore we can take an arbitrary linear combination of solutions of this form. There's an infinite number of these, one for every value of n. And we can take an arbitrary linear combination with arbitrary coefficients, and they'll still satisfy Laplace's equation plus 3 out of 4 boundary conditions. And now we can see if we can determine these unknown coefficients capital B to satisfy this last boundary condition. Again, to emphasize, Laplace's equation told us the separation constant here and here had to be the same. The boundary conditions told us that these separation constants were quantized. That is, the homogeneous boundary conditions, the 3 out of the 4. Then the last boundary condition is going to allow us to fix these unknown coefficients. The last boundary condition then says phi at x and y equal to L, which you just plug in, is equal to phi naught. But if you think about capital Bn times sinh n pi, this whole thing is like a Fourier sine series. So now you can see why we did Fourier series first, because we can use our knowledge of Fourier sine series to tell us what the values of b sub n times sinh n pi have to be. Since we're trying to establish the value of phi from x equals 0 to L, and this is a Fourier sine series from 0 to L, in order to match on to what we talked about before, we extend this to be an odd function of x. We take the physical value plus phi 0 between 0 and L, and we extend it, we pretend that there's a region between minus L and 0 where the value of the potential is minus phi naught. Then we can use our usual formulas. There is no cosine term in this Fourier series because the function we're expanding is odd. We can calculate the coefficient of the Fourier sine series, which is sinh n pi times this b sub n we've defined here, in the usual way, and we find that this combination has the value 4 phi 0 over n pi for n odd and 0 for n even. This is exactly an example of the Fourier series we considered when we were talking. So therefore, we have a solution. Phi of x and y is the sum over all n odd, where n is an odd integer, 4 phi 0 over n pi, 1 over sinh n pi, sine n pi x over L, sinh n pi y over L. This is actually a solution. It may not be a solution of a form you're used to. You may be used to a solution that's a polynomial or a simple trigonometric function. This is the solution of the Laplace equation subject to the boundary conditions in terms of a Fourier series. But we already know that a Fourier series can be used to evaluate, subject to the Dirichlet conditions, the kinds of functions that we want to find. And so we can rely on the fact that this is a smooth enough function so that this Fourier series makes sense. So this is the kind of solution we're going to get for analytic solution for partial differential equations. But in fact, we can actually plug in for values of x and y, and we can actually plot or solve for what these values look like. In mathematics, here's what a graph looks like. This is a three-dimensional plot. The value of phi is on the vertical axis. Here's x, here's y. The value of the potential is strictly 0 on these three sides, and it goes up to the value phi naught up here. So it's like climbing a mountain. And this seems like a perfectly reasonable value, a perfectly reasonable form for the solution, if you think about it. That means the electric fields actually are the gradients. They look like this. They're the perpendicular lines. At the level curves instead, here are the level curves. Phi equals 0 all the way around this side. Phi equals phi naught. If I choose it to be 1 up here, just for simplicity, it's 1 here. Here are the level curves of phi equals 0.8, 0.6, 0.4, 0.2, and 0.1. And in fact, if you evaluate it right at the center, you find that the value of phi at the center is actually 1/4. It's the average of its values on the outside. Suppose we had an arbitrary set of boundary conditions where we set one potential phi naught here, a potential phi 1 here, a potential phi 2 here, and phi 3 here, where phi 1, phi 2, phi 3, and phi naught are all arbitrary, not equal to 0. How could we express the solution for this in terms of what we've already done? Well, think about it this way. We can imagine writing phi as the sum of 4 different values, 4 different functions, phi a, phi b, phi c, and phi d, where each of these satisfies Laplace's equation, but each one satisfies it for a different kind of boundary condition. Phi naught here with zeros, phi 1 here with zeros, phi 2 here with zeros, and phi 3 with zeros. And by linearity, the sum of all of these also satisfies Laplace's equation with exactly this boundary condition. If we put that together with what we found out before, we'll find that the value of phi right in the center is exactly the average. And that's a general property of the solution of Laplace's equation.